Today we're all here together to discuss AI topics like all across the board, but in the context of a very exciting company called Tenstorrent. And with that in mind, I just wanted to first do some introductions. I guess we can first start with Ljubisa, who's the CEO of Tenstorrent, and he can give us a bit of information about what the company does, what its vision is, all that kind of awesome CEO stuff for a bit.
Absolutely. So thanks for the introduction, Yunus. I co-founded and am the CEO of this company called Tenstorrent. So we've been around for about 4.5 years now, and with the stated goal of building computing machinery that's specialized for machine learning and other similar data-centric computations, hopefully enabling the rate at which model training and inference happens to sort of really go to another level, be 10 to 100 times at least faster than what's available out there today. The way we're working on achieving that is by focusing on enabling fine-grained conditional computations, enabling deriving full benefit out of dynamically occurring sparsity in models, and finally building computers that are bigger than anything anybody else has built so far.
Sounds awesome. Yeah. And very key, right? Because it's so the demands on compute are so heavy from AI that any kind of step function change in the hardware space will definitely reverberate for a long time in the AI domain. Definitely.
So far, it's been the case that step functions in the hardware space cause step functions in the overall application space, and the growth of compute demand is still explosive. So we're hoping that we do bring about a step function in both domains.
Yeah, exactly. Cool. That's great. And we also have on the call Jeremy Barnes, who is from Element AI, the CTO, in fact, of Element AI, and I guess has a very unique perspective on how hardware can have an impact on AI, I guess. Jeremy, do you want to quickly introduce yourself?
Yeah, sure. So as Yunus said, I'm the CTO of Element AI. So we do fundamental research, applied research, and we bring it all the way through to products, which we bring to the market. So we get to see across all of the different phases of commercialization, starting from the academic all the way through. And we also do it across a bunch of different problem domains. So we obviously need a lot of compute in order to power that, but we see a more general picture of what there is in general about compute there. And interestingly enough, I've known about Tenstorrent for a very long time because I was actually involved in a little bit of helping some of the investors look at the company in an earlier financing round as well. So that's when I met the fantastic team, and got pretty excited about it then. And I think they've certainly done more than I expected in between, and so now I'm even more excited about it. And definitely step functions are something which, when you can bring them about, they enable people to think about things in a different way. And they enable new kinds of applications to be built, and those who can do those quickly can get a real leg up on their competition and make things a reality, which was just a dream before. And so anything like that that could happen, especially something which is not coming out of one of the big players, but something up and coming, is super exciting.
Mm-hmm. And could you give me a bit more, give us, I guess, the audience a bit more flavor about Element AI? It's a very unique company in a way. It's it's not an outfit that does kind of specializes in one thing, but it's actually almost like a horizontal outfit, right? It has a lot of scope that actually takes AI research and productionizes it in many different verticals. It's a very interesting business model, and it probably allows you to actually really see the trends in terms of productionizing AI. So could you talk a bit more about that actually?
Yeah, so I mean, the core of Element AI is really our research lab. We're a research lab, and the research lab, we have both a fundamental research lab where we interact with the academic community do fundamental research ourselves, which is directed by our product priorities. And then we have what I think is our superpower is our applied research lab, where we take the work that either our own teams have done or that other teams have done. We match them up to customer problems. We look at scalability and things like that, and we bring them to the market. And we do that in a few different ways, both by building solutions and also by bringing them into products as well. So there's a broad spectrum. We get to see both all the different stages of commercialization from very early to in the hands of the customer and scaling, but we also get to see across a lot of different problem domains and verticals as well. So from that perspective, we have a very broad perspective on what's going on.
Awesome. Yeah, we'll definitely touch back on that, I guess, like when we talk about the trends and stuff in ML. But I guess I'll finish the introductions by introducing myself as well. I'm Yunus. I have been in the ML space for a long time now, actually. I'm getting old without even noticing. It's bizarre. I basically finished my PhD in Cambridge in 2011 in machine learning. And since then, I've just been doing a lot of applied AI stuff in different verticals. So I've actually kind of been doing what Element AI does on a personal career trajectory way, right? And I've done a whole bunch of different applications, actually. I've done like high frequency trading stuff, which actually involves actually the hardware is really important there, weirdly, because you have to be like microsecond, like every microsecond matters in terms of inference time. I did some of that, and I then switched gears and came to the Bay Area and worked at a computer vision company called Vicarious, which is still around, for a couple of years. And then I moved, and there it was like, I got a really broad perspective on the current state of deep learning and computer vision, which was very, very useful for me. And then we basically, with one of my friends from Vicarious, we launched that like Comma AI, which is like a self-driving car startup. So I was there briefly. And then after that, I actually did some general consulting work and ended up at Uber AI Labs, which is like what geometric intelligence became inside Uber. And it gave me a chance to actually reconnect with some people that I actually worked with during my PhD. It was really cool. And now I'm actually like launching something new. So it's like a stealth thing that I actually absolutely cannot talk about, but it's also going to be really cool. And it's in a more, it's actually in a completely different application area of ML. So that I've ever done before. So I'm like a beginner again, which makes me feel really good. So I definitely have that kind of high level view of what's going on in ML and stuff as well. So with that in mind, shall we talk maybe about, maybe just like as a soft like introduction to the whole thing, like the explosion in deep learning, right? How did it come about, right? Why is it so significant, and what kind of impacts is it having right now, and what will it look like over the next year or two? So Jeremy, you want to take that, given that you're Element AI CTO?
Yeah, sure.
And I can definitely discuss it with you too.
I think Jeremy is one of the few people that were doing AI and deep learning as it was exploding, and didn't kind of join in on the tail end of the spike in popularity. So I think it'll be really interesting to hear his perspective on the whole thing, kind of from the eye of the storm.
You are in the eye of the storm, exactly.
Certainly am. And just a little anecdote to start that off. My first company was an NLP company, which this was pre-deep learning. And we actually hired one of the people who wrote one of the initial deep learning papers with Jeff Hinton, and immediately decided it was too hard, all this stuff he was talking about, and got him to work on writing heuristics. So that was a really big fail there. We had the opportunity to get ahead in deep learning, but we didn't recognize it for what it was there. So we've made up for it since. But it's interesting to see it's not just a question of the technology, it's a question of the timing. And to be honest, at the time, back in 2007, deep learning, neither the know-how to make it work effectively or the computational capacity was really available then. So it's something which I think has come about, partially because a lot of people believed in it and they kept the fire burning for long enough for the hardware to catch up. But also it's a question of fairly similar algorithms. I mean, obviously the architectures are evolving a lot to be able to solve different problems, but a lot of the fundamental algorithms and how they're trained is not that different these days. But now, instead of thinking this might work, we know it can work. And so that changes completely how people think about it, because they understand that most anything that you can represent inside a computer, you can process with some kind of a deep learning architecture. It started off with just images and things like that, but now it's sequences and things that have more structure. And with attention mechanisms and things like that, you can start to look in simultaneous places and deal with a lot more complexity and so on. And so people are starting to understand, these algorithms, they work, but they understand how to take them and map a problem onto a deep learning problem. And then on top of that, obviously, there's a computation, which is, there's enough computation to make it happen. You see in language models, for example, that you need a very, very large number of parameters in order to start to get good performance. And we still haven't found a limit to how many more parameters you can add to make it work. Yes. And on top of that, the ability to understand how the data aspect of it works, how to do combination of semi-supervised or unsupervised pre-training, fine-tuning, and things like that. So all of that know-how there. There's a set of tools, and rather than inventing new things for each problem with deep learning, deep learning is now a question of, we know that these algorithms can do these things, and we know we can put together the components of the solution to something that's probably going to be able to work. And so that's driven this idea that deep learning is not a science project anymore. Deep learning is actually a very viable solution to problems which we know can be solved because we can do it in our head, but we were unable to figure out a way with a pure engineering solution to do it. And so it's opened up this amazing range of applications that weren't addressable before across almost every business domain and every human task, really.
Yeah, it's actually really interesting that you mentioned NLP. I think NLP is a very interesting area where you can go from like an academic paper almost to something that actually works in production quite easily. And I mean, I'm also a co-founder of an NLP company called AMPLIFY Technologies, and they're actually it's very impressive. So usually in my experience, it's been quite difficult to take like a research idea and put it straight into production. But like in this particular instance, it's relatively straightforward, which is very fascinating, a very unique thing for NLP.
Well, you find sometimes that you have 100 lines of Python are the only thing that you need to create the structure of the solution and make it work. And that's just drastically better than it was not that long ago.
Yeah. And the few shot learning stuff that you can build on top of pre-trained stuff is also really key. I mean, the pre-training has become very, very reusable, which is interesting. Yeah.
That depends on the domain. I'd say that in some domains it's very usable. In some domains we haven't really figured out what the appropriate pre-trained representation is. Because if you look at the different domains like NLP, where pre-training is super easy, or natural images where pre-training is super easy, versus others like forecasting, or where there's no obvious way, you see that the progress has been made a lot more in those which do have a natural way to pre-train.
Yeah, exactly. So, I mean, shall we maybe talk about, like, in terms of the trends in ML, what are the hottest areas, like, in your mind right now? What's the top, like, 5?
So I'd start with natural language processing for sure. That's something which it's becoming cracked to a level which is approaching very, very good human writing. And it's also been able to be packaged up in a way with a fairly simple interface that can solve a vast variety of problems as well. So I think we're going to see just, if you look at the number of things that were built on top of the GPT-3 API, for example, we're seeing just this amazing explosion of application areas that use it. So I put NLP number 1. This is obviously very subjective. We were talking about robotics as well. So robotics is a big one. Not just the traditional robotics, things of being able to have base perception and some amount of planning or things like that, but the ability to we're starting to get a handle with reinforcement learning on being able to co-design robot and its environment and the task that it's working on together. So we're just scratching the surface of that, and that's going to have big impacts. I would say using AI-assisted design is a huge one as well. So using AI in order to optimize the designs of things, and you're using reinforcement learning to optimize it, using simulation environments in order to test things, and being able to get to these incredibly highly optimized designs without you needing to actually build stuff. I think that's
design in this context. Is it like what kind of area is it like?
So it's been used a lot in sports, for example, in different kinds of racing, Formula One, but also when you do, that comes from there because that's where the innovation is and there's money, and they really need to get the extra edge. Yes. But if you take that, if you're innovating on streamlining of something that you're doing for a race car, you could use that to streamline the hull of a cargo ship or something like that. So you see that the application areas, although they're starting there, they can be much broader and they can go much further.
That's right. So it's almost like the whole area of like Bayesian optimization, black box optimization, gray box optimization, that kind of stuff, where you use like a simulator to help you guide the design parameters essentially.
So Google's actually brought out...
and in particular, I like it
as well, which I thought was fascinating.
Brought out which?
Based on RL. So Google's brought out a chip design assistant that's RL based. So they enable you to use RL to build processors essentially. And I'm not sure if it's the case. It's kind of retelling what I've been told, but they've been sort of looking at using RL to design to work on the TPUs, which are themselves accelerating, I guess, part of the process. So it's at that point it becomes a bit of a
recursive, right?
Recursive thing, yeah.
yeah, interesting.
And I think apparently, for example, I heard somewhere that NVIDIA are one of their own biggest user of their own internal cluster in order to help design their next generation of chips. So absolutely, there's some recursiveness happening there. And I'm sure that Tenstorrent, there's something similar going on as you start to scale out too. So that I find super interesting. There's obviously all the vision applications. That's something which has been relatively solved for a while, but now we're getting to the point where the reliability is becoming important, and moving from just being able to do a decent enough job at recognizing things to getting to those 99.999% type accuracies that you need in order for things to cars to be safe on the road. So I think there's a lot of work still to be done there, but now we know the techniques. It's a question of improving them. And I'd say maybe the other place which is a bit out of the blue is forecasting. There are just starting to be some deep learning approaches which are cracking the forecasting problem. That is extremely important in the context of COVID, because the previous forecasting models, which were used everywhere, they often need 7, 10, 15 years of data. And there's just this massive discontinuity in almost every data set that happens with COVID. So trying to figure out how to take forecasting and make that work when there's no continuity in the data set for almost any of them, that's a problem which deep learning we're starting to see is being able to help start solve. So that's maybe other people wouldn't have that same one on their list, but I find it super fascinating to see what's happening there.
Yeah, exactly. That's interesting that you said forecasting. So, I guess you can view a lot of stuff as just forecasting. I guess like one area also that's I think becoming hot is biotech and medicine, right? I think there's I can see that trend kind of happening now. You also saw the announcement with AlphaFold that happened very recently of the protein problem. Very impressive result, actually. That one, I think in my mind is much more impressive than Go. Because that has much more impact, because I'm like very impact driven, right? But it's that's an interesting one. Any thoughts on that, on the medicine end? Or
well, for me, that's a little bit part of the using AI to assist the design process as well. Yeah. In the end, that's a different application area for similar kind of techniques there. I actually have only skimmed the AlphaFold, so I'm not sure exactly how they did that, but for me, that's a general set of techniques that you use to speed up the design process so that you can test more candidates more quickly and iterate to a solution more rapidly.
Sure. Yeah.
So it seems like sequence analysis models that were sort of sprung into existence in NLP are being inherited there, right? And it's one area that at least we've been seeing there's a lot of interest in enabling transformer models which exceed in size and sequence length what's been brought to bear in NLP. So especially in terms of sequence length, they're looking at, because I guess here you're looking at sequences that are relevant to the biological world where it's either proteins or it's genes or, and then the worst case lengths there are quite impressive, right? So they're looking at 64K sequence lengths and 128K, and that's apparently part of what's lit a fire under all of this recent research into making attention more scalable and bringing it down to closer to linear scaling from the quadratic that it is now. So that's one area that we see as considerable opportunity for hardware people to sort of enable next steps. And my mind's kind of blown that 2 out of the top 3 in Jeremy's list are RL. It's perhaps it shouldn't be, but for some reason I get the impression that RL gets a little bit less hype and airtime than some of the other areas, and it could be just sort of based on where I'm looking. But for people building computers, RLs are really different and interesting challenge because of these simulators, and it's essentially 2 completely different sets of workload and with completely different characteristics, and it's often difficult to figure out which side is going to be the bottleneck, right? So it's an interesting problem to kind of build a solution that works for both and enables for some kind of dynamic reallocation of resources between what runs the simulation like a game and the part that's implementing the controls. So a very interesting area for us.
Yeah, but it's still like
the worlds are.
Go ahead, Jeremy. Go ahead.
The worlds are moving together a little bit. There's a convergence there. You see, there's recently people have published a differentiable rendering engine, differentiable localization engine, and things like that. So we're seeing that the same sets of techniques and the underlying algorithmic blocks are starting to converge between the two. And so I think reinforcement learning is interesting, partially because it is a bit outside of the mainstream. It's not just a straightforward application of exactly the same techniques. It's it's something which is more new. And so a lot of people don't go to it naturally because it feels a bit more risky. But that's where I think a lot of the potential lies is in things that haven't been as deeply explored yet. And will, as people start to take the first steps there and take a risk, we'll see that some things start to work and we'll be able to open up different application areas.
Yeah, but I mean, I have to say, it's like there's a huge overlap between RL and sequence modeling generally, because I think typically what you do is you have to, almost RL just requires a very fast simulator to work, right? Because you have to have lots of episodes of stuff to learn. And the only way you can build a fast, like model of your environment is usually through a simulation, especially if it's very expensive, which means you have to learn a simulator for an environment, right? And that's basically just sequence learning at the end of the day. So the overlap is enormous there with sequence learning. Yeah.
Yeah, I mean, I think in most cases, the simulator is designed, it's not learned. But to the extent where the simulator could be learned, that opens up a lot more application areas, because the development of a simulator can be incredibly expensive.
Yes, exactly. And it's usually non-differentiable, very non-differentiable. Yeah.
I'm quite impressed at the stuff that's been proven to be differentiable recently. Here, like just listening to Jeremy and enumerate everything, it's kind of
Yeah.
You know, I haven't had the chance to look into the details of any of this stuff, but just it boggles the mind that you can set up a differentiable sort of almost anything.
Yeah, I think that's where the trend is happening, in the sense that there's going to be a point where the differentiable simulators are going to be as good as the traditional ones, right? The reason people use the traditional ones typically now is because they're usually a lot more accurate, right? And turning them to be differentiable might be it's going to be a long process, but it's going to be very, very fruitful.
Or is it accuracy, or is it just because they already exist? You know, for example, if you're rendering a world, you know, games do that, you know, many, many times a second already. And so it's like, well, I'm going to take this thing that already exists.
That's right. They already exist and they're already very good. So yeah, that's the thing. Yeah. So I guess the, like, you can characterize, like, since deep learning has been around, there's been, like, I was listening to this talk the other day that, like, there was actually like I think it was Andrew Ng, was like two major, like, paradigm shifts in deep learning. One was like convolutional neural networks, right? Like the scaling of convolutional neural networks to have incredible applications in computer vision. And the second one has actually just been transformers for sequence modeling. And I mean, I'm gonna be honest and say I don't actually know much about. I've never really played that much with transformers that much in my experience. I've done a few, but so I'm definitely not an expert in transformers. And I was wondering, like, to get you guys' opinion on, like, how significant are they? Like, are they really a massive game changer in sequence modeling, like, compared to LSTMs or RNNs, right? What's your experience been in terms of, like, productionizing these things? And what are the hardware requirements to make them fast too? Yeah.
Yeah, so maybe I'll jump in first there. I am not an expert in transformers either. I just spend a lot of time on Zoom with people who are at the moment. So yeah, this is all secondhand.
Yes.
But you know, the basic framing of sequence to sequence type problems. What's interesting about that is really that the way in which you encode something is just much more natural than it would be with fixed length representations. And so, you know, all the solutions that they're starting with with RNNs and your LSTM type models and now transformers, they're all really evolutions on this path to, let's not just deal with fixed length sequences. Let's figure out how we can deal with things that have a variable length and a variable shape. Yeah. And I think it's interesting too, because so many problems can be posed as a sequence to sequence type problem. And especially because it includes a generative step, it means that it's not something where you have a single hard output. It's that you have a kind of a probability distribution across, all kinds of outputs. And so that allows some richness in the representation and the output there. And I think the most interesting example of that is you look at the GPT-3 API, which is really just, here is some text, and then take that and, generate some more text, which is in the same, in the same kind of, which would be a natural progression from that text. And there's no right answer at all. It could be, you could do anything. So a generative model makes a lot of sense there, but it's also such a natural way to pose so many of the different problems. There's something we can just do with our head. Even like a 5-year-old can understand if I start something, complete the sentence, and write something more for me. So it's this incredibly powerful abstraction, but it's also very simple. And by being able to use sequence models, you can start to pose problems in a way which are just natural and just totally understandable. So that's what I think is interesting about it. But as we said before, that transformer really is a way to parallelize LSTMs, and it's really the attention which is the main the main thing which is driving the value there. But as you said before, there are, like, it's quadratic. If you have a 64K sequence, you have to do these incredible calculations. Almost everything is going to be zero in those calculations, because you're only going to actually look at a very small things, but you're just calculating these, multiplications of very small numbers by trillions and trillions of times per second. And, I like to draw the parallel between, how much energy does your brain take to generate some more text on the end of something for a certain number of words versus how much energy is taken in
Oh man, that was
that
was my one. You stole my idea. I had that written down as an idea to put in the video, and you stole it.
Sorry about that. You can edit me out.
No, it's all good. It's all good. Please.
But yeah, that, and you look at that, they're just incredibly inefficient as compared to our brains. So I think, for me, there's two things that come out of that. The first is that we have orders of magnitude of efficiency to go. So, we look at what you guys are doing at Tenstorrent, and, orders of magnitude more efficiency is something which should be absolutely achievable. But also, I think that it's not just necessarily that you want to be able to do these multiplications faster. You want to be able to have different architectures. So you do need something which is adaptable and flexible. If you're just to create the fastest ever, ginormous tensor by tensor multiplication unit, you're probably missing the kind of architectural changes which you need in order to make this really efficient. And so having something which doesn't impose an architecture but can adapt to different architectures, I think is really important too.
Yeah. So sparsity is key, but like actually doing sparsity in hardware in a way that is counterintuitive, because typically what people have done, people try to do sparsity in hardware before, and it typically always loses out to just doing the dumb thing of like hitting a giant matrix in one cycle on a GPU, right? So that's the way the challenge. I guess that's where so Ljubisa, you want to talk a bit more about like how you can that challenge and like how you can overcome that baseline?
Yeah, absolutely. So I mean the way I think about for all that I know, it might be wrong or incomplete, but the way I conceptualize the whole progression from vanilla RNNs through LSTMs through models like transformers for sequence to sequence type tasks is that recurrent networks usually apply a compressive operation to the sequence elements as they come in. So you have some set of states, which is essentially a summary of everything you've seen before, right? And this summary operation is inherent to the architecture. Thus, you don't have a control knob that lets you leave a sequence untouched in parallel and not apply any kind of compression or reinterpretation to it, right? So I kind of view LSTMs and RNNs as very compressive, attempts at doing the same thing as what the transformer does, where the key difference is that into a transformer block with attention, you'll take an explicitly represented sequence, which hasn't been compressed in any way, and present the entire thing to this block. And then the block's job really is to look across the entire thing and discern learn to sort of detect and use some relationships between the sequence elements, right? Which are presented untouched, uncompressed, available to be viewed in whole. And so it turns out that this has worked out amazingly well, that results of models that use attention have for now outdone their cousins that were based on recurrent elements. And the issue though is that now that you've unrolled this whole thing and presented it in parallel, you are essentially searching any-to-any relationships across all of the elements, and this causes the huge explosions in computation. It also causes the many small numbers and near zeros and zeros that Jeremy was mentioning.
Yeah.
So really, for the time being, for just the next step of making transformers more efficient, the ideal solution is something that can kind of take a high-level view, discover where the non-zeros exist, roughly speaking, sort of mark up some regions of interest, let's say, and then hopefully do this in a very cheap way. So, definitely not by just calculating everything and then looking post-fact, right?
Yeah.
And if you're able
I love the way you use the expression high-level view from a hardware perspective. I'm like, I've never heard that expression from a hardware guy.
so it's because I'm operating in my sort of model level practitioner mode.
No, it's great. It's great. We're both software guys, so we always like kind of look at it on a high level. But yes.
Yeah. So what you want to do is kind of marry the two worlds and enable somehow creating a summary view of this block of interactions, let's say, between sequence elements, and then having taken that snapshot, then only you want to schedule computation only for the areas that are of interest. Right?
Yeah.
And there's been a ton of work over the last year to do this using existing hardware. And for the most part, it breaks down into categories of either just kind of random sampling methods. So you kind of try and take some shots, and like however they work out, you have a fixed number of shots and you're going to go with that.
Yeah.
Or else you go with some assumed priors. So there's been lots of work on examples where people kind of assume that words or sequence elements that are nearby, they interact more, and thus you're going to calculate relationships between those. But as you move away, then you stop. Both of them are kind of subsets, and I think not quite as good in potential as the idea where you actually you have a mechanism to kind of tell where there's activity and then focus in and compute around there. Mm-hmm. So what we've been trying to do is to enable the latter. And if you look at it at the hardware level, so now we abandon the high level view and go down to chips and transistors, and essentially what this means is that you need to be able to effectively use your computing machinery with very tiny blocks of computation. So the whole idea of big matrices and like a lot of structure and a lot of these assumptions that you can kind of optimize around, that's kind of gone and out the door. Yeah. And then once you're able to do that, you can take this high level snapshot and determine where activity is. But then because you don't know where it was to begin with, figuring out how you parallelize the work is difficult because you don't know how many hotspots there are. Figuring out how much space the result's going to take, again, is also difficult. Yeah. So as a general statement for hardware and low-level software, so for folks that build the infrastructure that you guys go and use, it's basically a lot of things that were predictable and could be handled offline. They all move into runtime, and they're uncertainties that you need to deal with very effectively at runtime. So that's kind of the, it's interesting that it seems like there's been a bit of a step back towards the LSTM style of things recently. So DeepMind's put out this paper called the Compressive Transformer, where they essentially, they run a portion exactly right like now with fully unrolled attention. But then as you sort of leave a window of interest, they start compressing the distant past, let's say.
Yes, into one.
In a way that's very similar to LSTM's conceptually, I think, right?
Yeah. That seems like sounds like a hybrid between the two, actually. Yeah.
Kind of, yeah. And I believe that that's really where it's got to go, right? Like ultimately you need, in order to have very long distance memories, you need a recurrent mechanism of some sort. Yeah. So unrolling forever clearly isn't going to work, even with the efficiency that we're hoping to build. So I think that as this evolves, it's going to be a mashup of LSTMs and transformers of some form, right?
Yeah. Well, I guess going back to LSTMs, you kind of lose the parallel nature of it, right? Like that's what you give away in the trade-off, right? Because then suddenly it's sequential again, so you have to like wait, you have to delay computation, so you compute that history. Right?
That's right. So it becomes sequential again, and it introduces the concept of all the past is now getting summarized more aggressively.
Yeah. Right. Yeah, that's right. Yeah,
but it's possible that we'll do it differently.
No, go ahead, Jeremy.
But it's possible we'll do it differently between runtime and training time. The real advantage of transformers is they enable the training to be feasible on huge amounts of text, because you didn't have to kind of have this infinitely long computation. You had to kind of wind up on the forward pass and unwind on the backwards pass again. You could kind of just do all that in parallel. So I think it's interesting too to see, if you look at, for example, what the attention heads are doing. Back when I used to do NLP stuff before, we had algorithms which would learn, using machine learning, they would learn, how do you take into account the direct object, and how do you take into account the next word and the previous word and the preposition and all of those things. And you find that there's attention heads doing exactly the same thing there. Exactly. And so clearly this is a general mechanism to learn these structures that were encoded before, and you're able to learn them. But more importantly, you can train them, and so you can you can both learn a slightly different structure and how to use it. And it's a training which I think is really important. But once you've done with the training, that doesn't mean that there's not a equivalent version which is vastly faster at runtime that you can transform it into afterwards if you for when you want to do inference on it.
Which I think that shouldn't be understated. I think training can sometimes be slow, but if you're productionizing something, like people typically care a lot about inference time, right? And if at inference time, I think the hardware can play a very big role in making it very, very, very fast, right? Because I guess the weights are frozen then, so you just know this.
Yeah, and often you can train it once and you can use it for a vast variety of applications with just some fine tuning, or flip out a few layers or something like that. And so being able to train something enormous one time is okay. You amortize it potentially over thousands of applications, which is good.
Yeah, which is very, very good. Exactly. But one thing I wanted to underline is that the reason transformers they superseded LSTMs or RNNs is precisely it's actually like a hardware reason, like fundamentally. I don't think there's a big algorithmic improvement there. It's just that you can parallelize one and you can't do the other one.
Well, it means you can use, instead of 1 billion parameters, you can use, 200 billion parameters. Yeah. And so as it turns out, to encode what we need to produce language, it seems like we need at least 200 billion parameters. And so, that just makes it feasible. I agree. It's basically down to finding a way to map it onto the hardware available that lets you use enough data to get to the right level of accuracy.
Yeah, but what I wanted to mention to this audience is that actually this is a case of software engineers figuring out a way to exploit hardware parallelism as opposed to the other way around. It should be the hardware guys coming up with the right parallel structures that software guys can use, right? They're actually hacking the hardware in a way.
Yeah, in practice, it ends up being meeting in the middle, which I guess is what's been happening. I'm curious what you guys think about the following question, and I've heard from a couple of folks, mainly out of the hardware community recently, the prediction that models are gonna the sort of task of training models and deploying them in production is going to split into 3 tiers, and the top one being training these super models, if you will, that are billions and trillions of parameters, and their superset functionality that's trained in a semi-supervised way, akin to recent NLP models. And then there's I've heard the expectation be stated, and I'm not sure I buy into this just yet, although I don't disagree either, that there would be a mid-tier of models where you either you sort of use distillation to learn out of the bigger model a particular task and reduce it in size in terms of memory and both compute. And then finally, you deploy something akin to what I think Jeremy was alluding to, like some lottery ticket hypothesis type thought process where you take a trained model and you discover a subset that's really just as effective before you actually coerce it into a production setting for inference. And so the theory that's been put forth is that this now begets 3 tiers of hardware, which is the part that's interesting to me, where you now need sort of data center fulls and shipfuls of computing machinery to train up the large models. And then there's kind of a second tier, which is going to be on-premise data center for most companies, where they're going to be consuming these big models that only a few places produce and distilling them into something closer to what they need. And then finally at inference time, you need like a much smaller inferencing widget for this subnetwork that you end up extracting for actually going to production and inferencing. And so I'm not sure how I feel about all this. I'm really kind of curious to hear what you guys think.
Yeah, so I think go ahead, Jerry. You go first.
No, you go first this time.
Okay, fine. Our cadence is identical. We just wait exactly the same amount of time and then go bang at the same time. I was going to say, like, I think you're kind of right about that. I think the one of the trends that I definitely noticed is like the whole pre-training thing, right? People base their stuff on pre-trained models. So I can definitely see step 1 being a thing in terms of like you have these like universal models that people can just base their stuff off of. right? But sometimes people just start from scratch too. I mean, that still happens. So I think I don't think it'll be like a universal transformation. Sometimes it just makes sense to start from scratch. Actually, a lot of the cases it makes sense to start from scratch, right?
So I know you can't say a word about your startup and
Yeah.
you know and you shouldn't, but did you start from scratch? I think that seems
yes, actually in this case I did start from scratch. Yeah. That's an example of starting from scratch. Yeah.
So you're old school.
Interesting. And
I'm old. Maybe I'm just getting old. I don't know. Maybe the young kids are just doing it the other way this time now, and they're gonna just like crush me or something. Who knows?
But I think it's that really comes to my point. I mean, I hate the worldview where there's three tiers. For me, that's a worldview built by people who work for large companies who want there to be a tier where only a few people can afford the data centers and things like that to train the initial model, and then they control who gets to have a still version of it, and then they can sell into this into the inference type of model to everyone, because it means that there's this kind of sense of if you're not big enough you can't do it, which is to me is terrible. It's removing the democratization, because I can fit on my laptop the data which was used to train GPT-3, right? But why should you need $100 million worth of hardware in order to be able to reproduce it? And if we look, let's just take GPT-3 for example, because it's an interesting one where Microsoft has exclusively licensed the model. If you look what's actually happening there, it's really associative memory, language in, language out. There's fuzzy associative memory, and it's got a generative capability too, but it's this associative memory. And so if you're trying to learn a new fact, it's learning things via gradient descent, which is a horribly inefficient way of learning a new fact. It basically learns about words, but it's horribly inefficient. And I think that if we are to say, okay, we want to train this, fuzzy associative generative memory, how could we do that? We'll find ways thousands of times more efficient than what we're doing at the moment with gradient descent to train it. So my expectation and my hope is that we will be able to have, most companies be able to create this kind of an architecture and this kind of a model from scratch, because we'll get to the point where the hardware is good enough that you can get, at some point it's going to plateau. More words is not going to cause extra performance, and most companies will be able to afford to train a model like that, so it remains democratized to some extent. So that's my hope there, is that we won't live in a world with these three tiers. But I think a lot of people would love for that to happen, because those who are big enough to be in the first tier to start off with, they have this just incredible barrier to entry for any of their competition. I just don't think that's good for the world.
Yeah, I think as time goes on, I mean, this is, I guess, like now more in the domain of like what the future, like kind of like the crystal ball phase of the talk. But I do think data efficiency will improve with time. Like I think it kind of has to. So I think I don't think we'll ever be in a point where everyone's stuck using GPT-3. I don't think it's going to be like that. I think it's going to be like there's going to be a bunch of different approaches that actually work as well, and we use much less compute, right? For that. So it's definitely
I fully expect that too.
It's very hard to say, oh my God, this is the way it's going at this point. There's a lot of uncertainty. So the three-phase approach, it looks like it might be going that way, but it may not end up that way at all. That's what I'm going to say. Yeah.
Well, if people convince everyone else that it's going that way and therefore it's not worth trying, it will. So there's a little bit of a self-fulfilling prophecy aspect here. But that's why I think different kinds of hardware and the ability to get the cost of a training run of GPT-3 down from the possibly $20 million it is now, down to something which is more accessible, is really important. And anything which will help us get there, I think, is going to have a big effect and a big improvement on the democratization of AI in general.
That's great. Yeah. So I guess let's talk a bit more about the future. I guess like in the next 5-year projections of ML, what's going to be the biggest thing, just prediction wise? I mean, you're happy to be completely off the wall here. What do you think, Jerry? Where do you see ML going in the next 5 years?
Next 5 years, what I think we'll see is I think we're going to hit a wall with a lot of the, we talked before about assembling building blocks. We know how to do deep learning. You can put together different well-known solutions to the different aspects, and you can come up with a viable deep learning solution. I think we're probably going to see that this standard gradient descent based model of machine learning, we're going to start to hit walls. We're going to find that it's either cost ineffective or it's unable to properly solve some of the problems, or that the data requirements are going to be so big that only domains where there's naturally lots of data available will be able to crack. And so I think that we're going to start to see a lot more people looking outside of the box and saying, we won't get there with just deep learning. We're going to have to do things a bit different. We're going to have to be, think about new ways of doing it. And so from that perspective, I think that the companies, for example, who are designing these massive accelerators just for deep learning, which aren't programmable, which aren't flexible, are going to find that, they suddenly, their market is shrinking because people are trying to do things and, do new architectures and things like that. So that's what I expect will be out of the box.
Interesting. So you're predicting that well, first of all, that we're going to kind of hit a wall with pure deep learning approaches. People are going to start thinking about different things, different methods. Like probably one thing I kind of think is kind of missing in the whole thing is, trying to get some level of control over the network, right? So say you want to build a system that does this, but slightly differently. So you don't know what to go. You can't go into this is software 2.0. Right? You can't. It's hard to debug software 2.0. Really hard to adjust it to your use case. Right? Because it's a neural network with a bunch of neurons firing, right? So if you want a slight improvement, I was you kind of have to start from scratch. And that seems like a very weird way of writing software. The cool thing about software is that it's modular and reusable. And that seems to not exist that much. I mean, minus the pre-training stuff, right? It doesn't seem to exist at a very granular level for deep learning. And I think that is going to be where people are going to look at next. And it's the same kind of concept applies to do hardware too, I think, in the sense that, if you just really put all your eggs in one network basket, then suddenly the field might move away from that and do something else, and then you don't have that big a market anymore. So it's really crucial to have that kind of modularity, as Jeremy said. Yeah.
And as a very concrete example, convolutions. Everyone loves convolutions. But really, convolutions, they give you position invariance. That's what they give you. They're this position invariant matrix multiplication operation. So they give you that for free, but it's not free because they add an exponent. It goes from n cubed to n to the fourth in order to calculate it, right? So you add this huge amount of extra computation. For a lot of things, maybe you don't need perfect position invariance, or maybe you can deal with it in a different way. But once you say you're using that, you suddenly lose the ability to do anything but. And so we're going to start questioning a lot of these assumptions there and realize that there are different ways of getting something similar that are a lot less expensive.
Yeah, that's right. Actually, I just came up with an interesting example for controlling the network. Say you train a GAN and it makes amazing faces. Right, so you've all seen those face demos where it generates. Say I generate an awesome face that I love, right? It's I want this face, but I want it with blue eyes, right? It's kind of hard to do that. You don't have that granular control over it, right? That's what I feel is really missing in the whole thing. And this is more of an academic statement now. So I don't even know how you can even solve this, but I feel like that could be a big focus point in the next 5 years.
But I think to me, it sounds like what you and Jeremy are saying is actually has, non-trivial touch points, right? It's the story with gradient descent. I'm kind of curious to I don't know that we'll necessarily do it now in the interest of time. I don't know how you guys are doing. We're 5 minutes over. I just wanted to double check that you're okay. So nobody's sort of waiting on pins and needles to wrap up.
We can, as long as I'm off by in 9 minutes, I'm good. Actually,
I'll just send a Slack and I can take another 9 minutes too.
Cool. So what I was gonna say was that I'm curious about what's behind Jeremy's statements about gradient descent. But I guess one way you can interpret it is that instead of having to propagate gradient all the way through this entire blob, right? That kind of does everything in your example, Yunus. So if it does It generates faces, it generates, like colors. You don't know where it does each, and you have to train the whole thing with gradient descent. I think one thing that's a fairly obvious next step is to introduce much more local error backprop, right? So like that still keeps gradient descent, but it removes the, removes the concept of just doing it through the entire big kitchen sink.
You have to make it local,
right? Like, and so that's, it's still kind of gradient descent, but it's one step away from backprop as it is today. And perhaps if you add in the further step of having some kind of like a non-supervised way of generating the local errors that get locally backpropagated, you get a totally different beast than what you have today. And now it has modularity. And on top of that, now it's very cleanly mappable into hardware. So like at this point, if you had modules like that, a lot of unnatural exercise that happens today where you need to collect all the gradient updates from a pile of places and average them all together and then scatter them back. And, like essentially a lot of difficult things in hardware then go away because you've now created what's an equivalent of a circuit block pretty much, which you really can just like statically lay out in some kind of spatial architectural way, and it can just live there and learn forever, and it's a very clean picture for hardware if we ever evolve to that kind of direction. So it's modular, it's friendly to hardware. It breaks some of the bottlenecks that you get today with the current form of, a backprop through the whole network kind of story. So I like that image, right? And
exactly. Yeah. So here's my thing is that I think there's going to be some kind of improvement in basically a modular generative model, right, of data that performs equally as well as like a non-modular one, right? That's my dream. I would love to be able to do that. Of course, like if you do the modularity wrong, then you're underspecifying your model and you won't do as well, right? But there's a very sweet spot there that no one's quite figured out yet.
So even the convolution thing kind of fits into this picture in that if you had, this perfect building block that's able to learn connectivity to the extent where it can discover the fact that you want position invariance and that you want weight sharing and that you're able to reduce, reduce the number of weights, like you both get more data efficiency and you get this position invariance built in. And so ideally you would be able to learn this as opposed to have it be a pre-assumed prior, like on convolution or like, the operation and attention today. So this is definitely one of the things that we've tried to enable with the way we've put our hardware together. So, and the thinking being that like to folks like you would essentially manifest a PyTorch layer or a TensorFlow layer that that's kind of this, very flexible learnable thing that if you can kind of instantiate it, and if the task wants a convolution, it'll become a convolution, right? And if it wants an attention, it'll become an attention. And that seems like, the holy grail in terms of what we could actually put forth, from the bottom of the stack towards folks that are operating at your level, right?
Exactly.
And that's what we've been trying to package up. So all of these things that I was kind of talking about before, all of this, finer grained computation, the ability to kind of deal with a lot of dynamism, like ultimately all of that rolls up and becomes this layer, which is a layer that will both learn a shape that's more amorphous than just, a grid of numbers that always get to be calculated. It also learns the kind of connectivity you need so that it can become akin to a convolution or akin to a, to something more close to fully connected. And that seems like it ought to open up some avenues for experiment, but I guess time's going to tell.
Exactly. And the key thing is, there's an interesting link to hardware there in the sense that if you know the modularity, then you kind of know the sparsity, right? And then the hardware can exploit that basically. So
definitely this sort of idea is very difficult to build on top of current hardware. So it's possible, but the amount of like general kind of performance hit and just sheer effort that's required to make it happen now is, both of them are quite bad.
It almost has to come from the software level as like a compilation directive or something, right? Maybe.
Just a lot of it needs to happen at runtime. So
oh, that's true.
You need to kind of, on current hardware, what it turns into is compiling a bunch of flavors of things, which then end up taking way more space than the original thing took and way more time to execute.
Yeah.
And essentially, by the time you're done, it's so prohibitively slow that you can't really retrofit it even into toy models of modern architectures.
Yeah. Exactly.
So we're hoping to make a dent in that problem, although it's it's a big problem, right? Like it's a multi-year roadmap type story.
Oh, definitely. That's a multi-year thing. It's like I think the interface between hardware and software is not quite. No one really knows what it is yet.
Well, there's a question of learning too. The ability to kind of learn the sparsity and learn how to make local connections. Everything, chips are 2D and they can sometimes be assembled in a 3D structure, but that implies locality has to have certain constraints in order for it to be effective.
That's right.
And so if you're able to learn how to learn simultaneously how to have the most local and sparse as possible manner of connecting, while not losing the ability to propagate gradients or to train things in a kind of an incremental manner. Then maybe they'll be able to learn to speed up its own training at the same time as it's learning the underlying function or something like that. I think in the inference case, we start to understand it relatively well on the different avenues you have to distill it down. But on the training part, it's still an open question. And I think there's a lot of potential from the ideas that Ljubisa talked about to make a big impact there.
Funny, we mentioned the recursion of the AI-assisted design. You can almost apply the AI-assisted design to itself as it trains, right? Like that recursion is like nuts, basically.
That's a path to the singularity. And,
that's how you build AGI. That's that. We can end it on a brief discussion of AGI. I'm gonna be controversial and say that AGI is a myth. I don't think it's well defined. So I'm gonna call it human level intelligence, or maybe even animal level intelligence. Clearly, much better than anything we have right now. So, but yes, it's a path towards that, whatever that is.
That's usually what I mean when I say AGI, although I don't really know the definition either. I'm kind of I've heard the acronym, and I guess I'm just regurgitating it.
But you've mapped it internally as in your mind as a human level intelligence thing.
Yeah. Or even dog level. It's exactly like the vague description that you just gave. Like something better than what we have now, and closer to intelligent animals.
Intelligent behavior, exactly. That's right.
Yeah. And from my perspective, it's really a question of it's something which is a little bit emergent. If this conversation was being had between 3 people with brains the size of Manhattan, it wouldn't seem very impressive. It was like, okay, this is a big conversation between these people with big brains. Like, what I think is interesting is that we can do, we have this pretty kind of it's interesting what's inside our heads in terms of how it's structured, but there's not that many atoms in there. There's not that many connections, and the fact that it emerges from such a relatively simple set of primitives and via connectivity or something like that, there's something which is emergent about it. And I think our attempts to emulate it with Manhattan-sized computing facilities is kind of missing a little bit of a point there, that there needs to be something which is emergent, and there's something which is graceful about the use of the amount of computation which is available versus what it outputs. So for me, AGI is not GPT-3 knows more about many topics than any person in the world. No person in the world knows all same about all of it. So it's got this incredible memory aspect to it, but you can't say it's intelligent because it's just regurgitating things. There's something which is not emergent about it, although it's super interesting. And so for me, that's the property. There's something that has to be emergent and it has to be graceful in its use of resources.
That's right. Exactly.
This image of a self-optimizing neural net that does sound exactly, it seems to me to fit your criteria, Jeremy, right? Like it's graceful and it fits my definition of emergent. And I guess.
But I guess
Yeah.
the loss function is important too. I think the loss function and just backprop is probably a bit too simple.
Well, and definitely the whole like training and, you know, training to a certain point and then inferencing, like that whole worldview needs to go away, right? Like, so it needs to be there needs to be a continuous loop.
Correct. Exactly.
There, right? And maybe it's a loop like the one that you described, Yunus, where like it's actually two separate processes. Like, you know, one is designing chips and the other one is using the chip to optimize
there's a total loop at all times. Yeah.
Or it could just be a neural net which keeps learning, right? Like I still don't get why why everybody's accepted this, you know, wall between training and inference is a done deal.
Yeah.
So completely. Yeah.
That's true. And did you just imply differentiable hardware? Is that what you were trying to? Is that what you're getting at now?
That's not the thought I had in mind, but maybe by accident. I don't know.
It's a beautifully recursive idea. I mean, imagine a differentiable FPGA. Which,
that's what I'm talking about. Yes, exactly. That could be cool.
In fact, that's been shown to work on small tasks, like to the point where the FPGA would learn, like there were examples where it learned to do a task by side effect, like via unintended coupling between wires, like that type of story. So it's been shown in you know, in microscopic examples type story.
Yeah. Cool. All right. Well, for that, thanks guys for the awesome discussion. I mean, this was very stimulating for me.
It was amazing. Yeah, I really enjoyed it.
Yeah, thanks very much.